Hello, good afternoon, everybody. Welcome back to our international conference, Applied Category Theory, Graph Operative Logic in Memoriam of Zbigniew Osiewicz. We will continue with our afternoon talks in this first day of the conference. And to start with the following talk, we have as a keynote speaker, we have William Page, dear friend also. Well, I will read a little bit about the biographical profile of Dr. Bill Page, and then he will talk about concepts of relative acceleration. William Page has extensive experience as a senior consultant to government, private, and international organizations. His areas of specializations include modeling and simulation of complex systems, design and development of information systems with very large databases and advanced web-based applications. His areas of expertise include computer algebra systems, multimedia databases, programming languages, operating systems, secure telecommunications, and computer networks. And he was a frequent correspondent and occasional co-author of Zbigniew Osiewicz. And he is from Kingston, Ontario, Canada. So let's welcome Professor William Page, and he will start now by giving us his talk about concepts of relative acceleration. Thank you very much. Please, Bill, go ahead.
Okay, thank you very much. I already feel like I'm experiencing what's called Zoom fatigue these days. It's a new ailment of people who are spending too long in front of their computer systems interacting in this way. But I think we can make it through the day. It's a very long day. And we have 3 more to go. So I am going to hope that my presentation is relatively short and easy, even though the actual paper is going to be more technical than the things I'll say right now. Before I do that, though, let me see if I can share my screen here and start with something else. Okay, so I presume that you are seeing this first page. So I wanted to make a couple of announcements before the talk. The first one is I wanted to mention that we do have an ongoing seminar, Zoom-based seminar, which is being hosted by Professor Cruz. And it actually started during the early part of the pandemic, as I understand it, as a means for Zbigniew and Jesus to continue discussions on physics. But shortly after we started to get organized for this conference, when Jesus mentioned that he had such informal seminar, we together decided that we'd like to continue it somehow. So we have been doing this, I think, roughly since December, meeting every 2 weeks on Wednesdays. But so far we only have 3 members. So I did check with Jesus in advance that it was okay for me to give this a little bit of an invitation, and I don't expect that there'll be a lot of people, at least I hope not, in some ways, because a small group by Zoom is actually somewhat more convenient. But by all means, anyone interested in discussing physics, especially physics of the type that Zbigniew is well known for, being controversial or foundational, mathematical, it would be very interesting to hear from you on this sort of ongoing seminar. The second thing is I wanted to mention is that I do have a little work in progress project of mine, which had to do with presentation that was given by Zbigniew in 2009 to a group called the Natural Philosophy Alliance. They are by no means mainstream physicists. In fact, they are particularly their goal is to look at major alternatives to conventional physics, and in particular, they are critical of relativity theory, of quantum mechanics, and a lot of mainstream physics. But it's probably sort of a comment on the difficulty that Zbigniew had in actually presenting his ideas on relativity, that he ended up giving a presentation to the NPA. And ultimately, I think he wasn't particularly happy with the response, but I did manage to get an audio transcript, and I asked him for a set of slides for that talk. And so I have been in the process of converting them to so online slides, like using Google Slides. So there's a link here, which of course you can't click easily. I guess I could put this on the chat or something like that, or I can do that later. But in any case, I was wondering if you minded that if I actually played the first slide in this presentation, because it's really very much on the subject of my talk. And if you bear with me, I hope that I've set things up so that that's possible. So it's a long talk. It's about almost 2 hours. And so first slide is about 5 minutes, I think. So if no one objects, I would like to play it because it does sort of present Zbigniew in very much the way that some of the speakers earlier today mentioned, I mean, as very personable and open and inviting, and very human. So let's see if this works. And certainly if some of this doesn't work, I feel a little blank, so I don't see feedback except for a few people moving their heads. So if anything does go wrong, just let me know.
Is listening me. Thank you to Greg Volk for inviting me. I was not sure what was really subject that I should talk about. And so I'm from Poland, born in Poland, educated in Russia in St. Petersburg University. And Yuri Kailman is my colleague from the same university. We are educated at the same university. I was educated in mathematical physics. So I'm rather a mathematician, not a physicist. And from my I think that from my education of mathematics, I always was interested in formulation of physical theories without any convention, without coordinates in terms of invariant concepts. Everybody is listening me, okay? But okay, and at the end of 70s comes to me idea to formulate special relativity without coordinates. As Lorentz, what is Lorentz transformation? Everybody know, of course, but how to formulate relative velocity between two reference frames without coordinates, and also understand what is reference frame without coordinates. And after I formulated this happens to be exactly the formulation of the Minkowski in 1908. And then from this definition of reference, I'm using reference system because my reference frame is not a basis, and definition of the relative velocity, I derived formula for composition of the velocities, and this formula does not coincide with what we have in all textbooks of special relativity, of Einstein relativity. I do not understand why it is so, and only 10 years later, in 2003, I finally understand why such situation is, what is problem with special relativity of Einstein, as Einstein was defining. What I should say more about me? Is that I'm interested in the application of the good mathematics to divulgation, popularization of good mathematics for students and in application as a sciences, and I'm organizing some modest workshops almost every year, and this year in Mexico, and this year in Pacific Coast in January. This will be 1 week starting 9 January, and everybody is invited. I like to invite very much Harry Ricker, but Harry, you live so far away in another coast of in Atlantic coast, right? Atlantic coast. So this will be not so easy for you to participate. So I prefer that you. Okay, Ricker. So I prefer that you ask me some. Yes. This is linked to my conference I am organizing, and I will be happy that everybody. This is a nice meeting of friends. Here with me is my girlfriend, and she helping to organizing this conference, Ilda. Okay, so maybe I here is just science subjective. I think that everybody agree. If somebody disagree, because if would be objective. Oh, welcome, Hilda. Do you have this? Okay, and also controversial subject is interesting. I'm a referee to many journals, among many the Foundation of Physics, and once this chief editor wrote to me that that they are publishing only non-controversial papers, and if paper is controversial, you need 5 referee reports, and really delay is almost 2-3 years for publishing. Then I proposed to him that he must change title of his journal, must be journal not Foundation of Physics, but Foundation of non-controversial physics. And then nobody is interested to read such a story because everybody is interested only in a controversial subject. Okay, so this is my introduction. Robert Kien is also controversial. So I don't like this name special. What means a special names?
Okay. So I hope that was okay, that you could actually hear the presentation. The presentation goes on in some detail, actually, to describe the theory of relativity that Zbigniew had developed up to that point in time. But like a lot of things with Zbigniew, this was an ongoing process, and I was actually part of the sort of interaction starting, well, a little bit before the NPA conference, but after that, I became much more active in correspondence with email, and I met with Zbigniew probably once a year, sometimes in Mexico, sometimes at conferences in other places. But we usually spent most of the conference sort of working on ideas we had together, and only occasionally visiting papers, or visiting, actually attending talks at the conference. So the conferences were excused to get together. Unfortunately, these Zoom conferences aren't much like that at all. You actually have to pay attention all day almost to what's going on. Okay, so let me get back now to what I was going to do next. View presentation. Okay, so next. So I just wanted to show you some of the, like one particular piece of correspondence that was between me and Zbigniew. And the last paragraph specifically constitutes my invitation to this meeting, which was actually being planned back in 2018. And so he invited me specifically to come to Mexico this year for his 80th birthday. And he said, by the way, also, this is the 70th anniversary of Professor Jesus Cruz's birthday as well. And so I haven't heard that mentioned yet. And so I just wanted to add this to the slide, to my slide presentation, that I very much appreciate interacting with Professor Cruz, and I wish him a happy birthday, and thank you very much for organizing this conference, and also to all the other organizers of the conference at UNAM, with whom I've had privilege of actually working over the last few months to get all this in place. So thank you very much. So with that, let me actually get on to the things I was intending to talk about today. And as I said, this is kind of an overview, and I hope that what I'm saying will be sort of mostly a matter of summary for the actual paper that will be likely published in some way or another later, as current plans for possibly all of these papers being reviewed and included in a book. So I think that would be great. So what I'm talking about here is the notion of relative acceleration. Relativity usually focuses on relativity of velocity as being a primary concept, and it actually was seemed as a bit of an addition or afterthought to consider how to present acceleration in the framework of relativity, And it didn't really come until later in the development of the early development of general relativity, how to treat acceleration in this framework. But in the work that Zbigniew is doing, he's really been critical of the way these things are presented in relativity, and so it never caused me any problem when he and I discussed things. I never had problems sort of understanding his point of view and what he wanted to say. Of course, he's a very persuasive speaker, so that was easy to get past any skepticism. But he had a lot of trouble publishing ideas, and sort of ended up publishing them in odd places. But in any case, getting ahead of myself. So the paper is starts with an introduction to what Shevitz called Groupoid relativity. And Groupoid relativity takes quite a radically different view of the meaning of relativity compared to what's presented in classrooms and in most textbooks today. But relativity is an old subject, and so at least old relative to our modern world. It's a sort of foundational thing that is hard to argue against unless you take very close look at foundations, and this is actually probably more commonly done by philosophers than physicists these days. Let me get on. So, but this Groupoid relativity, as presented by Shevitz, actually has a very deep mathematical basis in abstract algebra, and it, to a large extent, it avoids geometry, in which is quite counter to the way that geometry, the way relativity is presented these days. And the goal that Shevitz is working towards, I think, is a complete and consistent relativistic dynamics, something which in some respects has actually eluded theoretical physics for a long time. We have in practical terms, like for example, in describing the motion of the galaxy, or in say closely bound binary stars and so forth, we still make use of what are referred to as post-Newtonian approximations, and basically use Newtonian physics with general relativity implied implied in terms of additional terms in an approximation, rather than solving general relativity directly as a theory. And I think what Shevitz is was hoping for, was to get closer to what could be done with classical mechanics, for example. So one particular problem that was of very significance to him was the idea of center of mass. That is, like how to define a center of mass for two interacting relativistic bodies. And one of the last papers on his subject actually does accomplish that, I think. But on the way, he criticized and then provided an alternative to the way that acceleration was defined. And that's most of this talk is based on that paper. But in order to get there, I wanted to first of all start with some of the background to the some of the philosophy or metaphysics that is sort of fundamental to groupoid relativity. And this is just a quick summary of the abstract of the paper. So we need to present, or we want to present material objects as processes, as something which have time sort of built into them in some mechanical way. Some mechanical way, as in classical mechanics. How should I say that? As something fundamental to the notion of a material object. And also, we want to insist that all motion is relative, that it's a collective property of objects rather than being a property of an object in itself. And that the motion is something that can be composed, so that we want to insist that the composition of motions is uniquely defined, and so we want to ask the question of whether motion itself is a physical property, even though it's not associated with any one body. There's also the question of reciprocity in relativity, in classical relativity. It's basically assumed that that inverse motions are additive. That is, that you can subtract that the velocity of A with respect to B is exactly equal to minus B with respect to A. But it turns out that that isn't the case. What else shall we go? Right. So ultimately, Shevitz defines acceleration in terms of a Lie bracket, as opposed to the second derivative of a trajectory. We'll get to that. So Zbigniew was fond of pointing out that relativity is a really old subject, and that it was actually people like Copernicus who made it clear that relativity was fundamental to physics. It wasn't, in other words, it wasn't invented by Einstein. Only the only addition that was sort of fundamental to special relativity had to do with limitations of speed of light, which made it necessary to extend the notion of relativity considerably. But even Newton is referred to as having required the notion of absolute position. That is, like, as things being able to be assigned a position independent of each other. But in fact, it was recognized by people such as Henri Poincaré that, in fact, this was only a convention, that it wasn't a fundamental notion of classical mechanics. In fact, one way of summarizing the development of classical mechanics, perhaps, was Lorentz's theory of the electron, which was one of the last attempts to actually reconcile electromagnetism and mechanics prior to the actual development of special relativity by Einstein. But Einstein's theory of relativity started with the kinetics of Lorentz's theory, but it actually didn't say anything specific about the mechanics. It actually was neutral on whether or not things such as ether was necessary, and it took quite a few years before it became unpopular to consider ether as part of physics. So it's now considered sort of part of dissident physics, or of interest to people like the NPA that I mentioned earlier, but no longer considered part of mainstream. But at the turn of the previous century, physicists and mathematicians like Lorentz and Poincare and Minkowski and Planck all considered it to be essential, although but its understanding of it was strained by developments in electromagnetism, and so the possibility of getting rid of the problem by ignoring it altogether or making it unnecessary seemed attractive, I think. But let's see. So, in many respects, what Shevitz is trying to do could be seen as wanting to reset relativity back to about 1908, which was actually when Minkowski published his last paper on relativity. It was about 3 years after the paper by Einstein. And this paper by Minkowski, although it became some parts of these ideas that were presented in 1908 became sort of fundamental to special relativity later, or actually much more fundamental to general relativity. It actually was still rather strongly disputed in the early years about whether or not we could treat space and time as a single manifold. And so Minkowski is recognized as being the author of the idea that space and time should be considered as one thing rather than two together, two separately. But Shevitz is saying that a large part of what Minkowski was actually presenting in that paper in 1908 was misunderstood, or at least mispresented, presented with a different emphasis by his student Max Born. Minkowski died about 3 years after that paper and never really had an opportunity to extend that work. That was done by others. Einstein was one of Minkowski's students. But Minkowski was focused on what needed to change in classical mechanics in order to incorporate electromagnetism, and he wanted to extend it to matter. He wasn't really focused on relativity as a theory, but only as a consequence of these properties of matter. The subject, after Einstein's paper and the Solvay conferences that came a bit later, the development moved away from classical mechanics as being of lesser interest. And it was, I'm always kind of interested in a quote by Poincaré, which apparently was the only time that Poincaré met Einstein, was at this 1911 Solvay conference. And at that conference, Poincaré asked Einstein to explain what type of mechanics did Einstein use in his reasoning about relativity, and Einstein's reply was that he didn't use mechanics at all. And so that was like a shock to somebody like Poincaré. Poincaré continued to publish on relativity after that, but apparently never met with Einstein after that point. But I certainly wonder what relativity theory might have been like if Minkowski had been able to be there to continue his work. Yes, okay. So I'll just skip some of that. I'm just pointing out that Dr. Shevitz had quite a few papers as a mathematical physicist on numerous publications, numerous mathematical subjects, but he had trouble publishing papers on relativity. But in spite of that, he incorporated many of his ideas into his teaching as part of graduate courses in electromagnetism and thermodynamics and relativity. And some of these documents, although they are important class notes, have not yet been published officially. My own interaction with Shevitz was largely in my attempts to actually use computer algebra, which I have a much stronger background than in physics or abstract mathematics. But computer algebra systems do incorporate a great deal of differential geometry, and when used in the right way, can actually help flesh out calculations, and particularly to test assertions that are difficult to prove in other ways. And so I was often interacting with Shevitz with that point of view. And in this work that I was doing on relative acceleration, I was using the same approach. I was trying to carry out the calculations that he derived formally, abstractly, but in concrete terms using a computer algebra system. And in this case, computer algebra was quite necessary, because what I wanted to do was look at how the abstract definitions related to the much more common way in which relativity is expressed in terms of coordinates. And that's in spite of the fact that Shevitz was very much against coordinates as a means of deducing relationships. And in spite of that, it is critical to be able to reduce abstract mathematics to operational terms in order to test against alternative ideas. In particular, groupoid relativity is not based on Lorentz transformations forming an isometry group in geometry. But groupoid relativity is focusing on the physical relationship between two objects, not just as a result of measurement, but as a real physical property. And this question of whether or not there are properties, whether properties exist that aren't measurable, actually enters this question, enters enters the picture fairly early. Let me just quote from Planck. As I mentioned, he was quite critical of special relativity early on, but also a strong supporter. And Planck insisted that relativity didn't get rid of the concept of physical absolute properties, but instead it required that we define what we mean by absolute properties more carefully, so that we could actually express relativity in terms of these absolutes. And in the later years, Planck wrote a number of sort of philosophical papers on this subject. So the word absolute is being used here as meaning free of the observer, like not dependent on any observer. There's another word that's also important, is notion of being intrinsic. It's like naturally belonging to something, or being an essential part of something. But intrinsic things are not the same as being, not the same as absolute things. So what else? Well, this is getting to be longer than I thought, and I want to skip ahead a bit. Let's get to the point. So, Zwinger's theory recognizes as absolute the concept of an event, and that event is something that does form a manifold, but we should not think of it as being necessarily in space or in time. So he objected to the name space-time as being incorrect. And in particular, in this theory, the notion of space is replaced with what he referred to as position space, which is actually a mapping from space-time, from the algebra of space-time into the algebra of space. And this is expressed formally. Let me skip ahead. Something like this, that what we know as space depends on the choice of reference, X, and a body, a physical body. And with respect to that physical body, there is a concept of place, of being in some place with respect to that body. And similarly, there's a concept of time as being a set of hypersurfaces over this event space or event manifold. let me get ahead here. Okay, so in the paper, I go ahead and having described Zbigniew's approach, I want to actually review the way things are presented in contemporary relativity. So let me skip ahead. Contemporary relativity starts really with the Lorentz transformations. But Zbigniew pointed out that one can treat the Lorentz transformations as a system of equations and then actually ask the question, well, what is the parameter v in these equations? Like what we usually write down the Lorentz equations assuming what we know, what we mean by velocity. But in fact, if we solve these equations, we get rather strange looking result. So we get this expression 3 here, which is expressed in terms of the differentials related to 2 coordinate systems. And this expression does not have the form that you would expect velocity to have, except in the Galilean limit. In the non-relativistic limit, it actually looks like the difference of 2 ordinary velocities. But for finite speed of light, we get something rather different, something that we can't easily reduce just to a difference of 2 velocities. It turns out that this is related to the fact that the Lorentz transformations are not uniquely parameterized by a single vector, by the velocity. In fact, this was a sort of major part of Shevitz's criticism of special relativity, is the fact that this isn't recognized in the conventional presentation of relativity. That in fact, the velocity that is used in the Lorentz transformations and which obeys axioms of special relativity as defined by Einstein actually are not a relationship between 2 bodies. They require a third reference frame in which to actually express the notion of relative velocity. And so ultimately, Shevitz argues that special relativity didn't succeed in getting rid of the ether because it's easy to just take the ether as this third privileged reference frame or preferred reference frame. This discussions along this line still persist in relativity theory. In fact, there are proposals to take something like the microwave background to be the frame from which to define the relative motions. But what Zbigniew really wanted to do was to get rid of the ether altogether and to define velocity in a binary way. So, we're going on very long, and I think I'm going to have to stop at this point without actually getting very far along the subject. The main point is that it's been difficult, I think, for Shevitz to present this to people with conventional theoretical physics background, because theoretical physics has gotten so far away from insisting on the notion that physics is about what is real as opposed to what we can measure. So that, of course, the idea that we should focus on only those things that we can measure might be considered to be one of the sources of problems for the progress in relativity towards solving problems like calculating the center of mass for many interacting bodies. And it might even be the foundation of problems in such as the origin of dark matter and the motion of large-scale motions of the galaxy and so forth, in terms of alternate theories of gravity that would account for motion, fully relativistic calculations with respect to some type of center of mass. And the center of mass depends now, in Zwignev's theory, on the relative motions of these bodies as well. So that remains to be seen, and unfortunately, Zbigniew is no longer with us to continue this work. But I hope that more things are done in this way, in this direction. And I'm optimistic, actually, that we do have some ways forward. Some of the talks later today, or continuing after me, do deal directly with notions of relative acceleration, and particularly Dr. Coxan will be talking about these same ideas. And there's also a talk about relativistic dynamics. So I'm very much interested in stopping at this point, maybe answer a couple of questions, and continue to be able to listen rather than rattle on for too long.
Thank you very much, Dr. Bill. So if any of our attendees has any questions, any comments for Dr. Bill Page, you're welcome to ask any questions or make any comments just right now.
Yes, Bill, I'd like to I'm wondering whether, from what you say, there's no real contradiction between Shevitz non-associative relative composition and just a matter of you have to use a third body in order to unite the two theories. So there's nothing contradictory about Shevitz point of view as to regular special relativity.
No, I don't think that what he's saying is contradictory, but it is critical to understand what this implies with respect to sort of the ontological status of the notion of relative velocity. In particular, people like Abraham Unger pointed out that composition of velocities in special relativity is not associative. And non-associativity means that, for example, if we have four bodies and we group our compositions differently between, say, the object A and object D, we can actually calculate two different possible relative velocities. And it's entirely consistent. I mean, that's exactly for example, what Dr. Shepanova mentioned this morning about interest in non-associative group theory, for example, which mathematically makes perfectly good sense, but from a physical point of view causes problems, right? That we can no longer depend that we have a simple and clear notion of the velocity of one body with respect to another, because exactly what that velocity is depends on a third body. And so if we're interested in using the relative velocity to contribute to our understanding of, say, the center of mass, or the then we immediately run into problems, and that things like center of mass become a global property instead of a locally definable property. Is that an answer to your question?
It clarifies it some. I'm still not absolutely clear about exactly why the third body.
Knowing what the question is usually more important than actually knowing what the answer is, I think.
Thank you very much for the question, Garrett. Thank you, Vil. Now we have another comment and question by Gregor M. Coxon. So please, Gregor, make your question.
Gregor Kochan. I have a question. I can see equation for Osiewicz acceleration. Could you show something? Thank you.
Yes. Let me just bring this up again. If I look here. Yeah, so this slide, which is quite a bit ways on in the presentation, describes the intrinsic definition of acceleration, or sometimes would be called for acceleration, in terms of the Christoffel covariant derivative. But
okay, thank you. What about explicitly derive formula? It's not general, but concrete. I mean, I want to comparison this acceleration for example, Einstein acceleration on another acceleration, and I can't in this form. But I know this problem. Okay.
Well, yes, well, in this form, let me go one slide further. So the nabla here is the covariant derivative, and provided that we are willing to make some assumptions about geometry, in particular, if we can assume that the torsion of the connection is zero, as it would be in a Christoffel derivation, then we do have a relationship between the Lie bracket and the covariant derivative. That's precisely what we mean by torsion. So this is saying that there is a relationship between Odyssevich's definition and the conventional definition, but the relationship is similar to what I started out mentioning about relatives being defined in terms of absolutes. So here we have the same thing happening again.
Thank you very much, Bill. Thank you, Professor Colson. Well, so we will finish now with this interesting talk given by Bill Page. So thank you everybody for continuing with us. This has been a long journey, quite exciting, but also quite tiring sometimes. It's tough, so but quite interesting talks. Now it is the turn of Gregor Colson. He will continue now exposing his own views, and he will talk to everybody about relative, binary, ternary, and pseudo-binary 4D velocities in the special relativity. So Gregor, please, the stage is yours. So if you can share your screen, and if you want to start your talk, go ahead. Sorry, you have to open your microphone.
Okay. Do you see my ekran, computer, slideshow?
No, we cannot see your screen. So
No.
You can
Okay.
share screen. That's right. We are. So we'll stop watching your screen.
Sorry.
Yes, we see the screen with Einstein formula.
Okay. It's good. And now?
And now we see your presentation.
Presentation. Okay. And
because it is very difficult because you cannot see what we see.
Now it's?
Yes, it's full screen.
All screen. Okay. Do you see my mouse arrow is very important? Arrow for mouse.
Yes, it can be seen.
Okay, thank you. I talk about special relativity, relative binary, ternary, and pseudo-binary 4D velocities in the special relativity. In part one, I show covariant Lorentz transformation. Basic concepts I show firstly. Well-known 3D velocity is, of course, derivative position respect to time, and we derivative respect to street or canonical parameters. We get versor who normalize to unit. In diagram, ordinary relative velocity, of course, is this red vector who connect ending of the vector first and to body. In Minkowski velocity, space-time, four-dimensional velocity, we defined similar for derivative for position according to self-time, and we get for velocity first component, time component is gamma c, and three-dimensional component gamma v, normal v in three-dimensional. Gamma component, of course, this formula. Space-time, I use signature plus for time and minus for space. Geometrically, this for velocity I called here Minkowski velocity. Exactly, Minkowski velocity with blue vector, blue 4 vector, new alpha is exactly versor because tangent vector versor because he normalized to speed of light. We have two fundamental types of relative velocity in special relativity in four-dimensional language. For example, relative binary type. Of course, if we subtract two velocity for two body 1, body 2 velocity, we subtract. But exists more complicated notion, ternary relativity, ternary relative velocity, which depends to observer velocity, is the third velocity, body 1, body 2, and observer velocity. Thence we called a ternary type. If we can something different, for example, simplified ternary, we can call it pseudo-binary type. Of course, relative velocity by default is a space-like vector, which square, b square, is less than 0, but exists to time-like relative velocity. For example, zeta square higher than 0 and equal s square. Canonical binary relative velocity. Exactly Osiewicz binary relative velocity. I called to Osiewicz-Bolus binary relative velocity. Definition, exactly definition is, it is subtraction to Minkowski velocity of one body and two body, but the first velocity we need division by gamma factor, and exactly means here. Let's go see it in reference frame of Ni alpha vector in the second, first body. For example, this velocity in this reference frame is obviously zero vector, but times component is C, but and body 2 mu alpha vector is here, and we divided gamma factor. Gamma factor is reduced, and we get simple four vector which have zero times component, but second component, free component, it's normal velocity. That's why binary relative velocity is the one in sense normal space-like velocity. Construction, geometrical construction of binary velocity done here. For example, relative velocity blue vector respect to green vector, we need construct orthogonal line to green vector. It's red line to the end at blue vector, and we construct this exactly binary vector. Red vector is exactly binary vector omega 1, 2, and another analogous we can construct omega 2, 1 vector. We see that this vector is not opposite vector, but this vector has the same value. History of binary velocity, I think, is the most important for us is the date 1988, because Dariusz Świerk writing master thesis under supervision of Osiewicz. I think it is proof that Osiewicz was the first scientist who defined this notion, but several scientists defined later this notion. Formal publication for Osiewicz it was 2014 and 2007. Yes. The covariant Lorentz transformation. We can parameterize Lorentz transformation B vector or two vector. For example, here, two time-like vectors, sigma and zeta. Sigma is frame first observer, and zeta is the reference frame second observer. Alternatively, equivalently, we parameterize Boost-Lorentz two vector, but first the same green sigma vector, and second space-like vector who orthogonal to green vector. Of course, exist inverted boost in language psi vector. Inverted boost is easy. It equal to minus psi. But if we use another parameterization for two time-like vector, inverse boost is replaced with vectors to place sigma zeta, zeta sigma. Of course, we can define Lorentz passive boost and Lorentz active boost, and check for graph, for example, convex and concave arrows. It doesn't matter. It's not very high important. Explicitly, form of covariant Lorentz transformation is here. Let's show only this first equation for passive Lorentz boost. It is very important equation. It is simplest way of writing the most general Lorentz boost of vector. It contains a general boost case of velocity transformation. That's why it's unified coordinate and velocity transformation. This is one equation, is very, very general and don't very popular. Let's see history of this covariant Lorentz transformation. For us, it's more important 1977 or 1978 when Krauss publication and gave a full solution in the form I show for previous slide. Of course, another scientist get this concept, but is very no in handbook. Like only I found only one handbook, SR handbook by some parents. Yes, let's go. Inverted velocity problem in the sense of calculating on Lorentz boost parameter. It's based on covariant Lorentz transformation. If we have Lorentz transformation, velocity mu to velocity beta, we ask about parameter zeta. Yes, zeta is unknown variable parameter which we must derive solution with this equation, which depend for three velocity sigma, beta, and mu. Solution of this equation done here. We see this is not simple, but very important. Two fundamental different approaches to relative velocity in boost scenes. First approach is well-known Einstein type approach. For example, it's ordinary Lorentz transformation of velocity mu. If we consider Lorentz transformation from green reference frame to blue reference frame, its lead transformation mu to beta. It's normal Lorentz transformation. But exist second scenes of relative velocities when we ask where we're looking for another reference frame, another velocity zeta, when Lorentz boost from sigma to zeta leads transformation nu to mu. Yes, it's something more active definition. Observation.
You have 5 minutes to round up your presentation, please. Thank you.
5 minutes only. Okay. Yes, this concept, ternary velocity, seems simple, but it's the same time is so deep that many Oziewicz reviewers were not able to understand it. Our peer reviews were guardians of the truth. Oziewicz 2030 about it talk here Alberto Gistow. Einstein-Minkowski relative velocity and Einstein-Oziewicz relative velocity. Because I have only 5 time, I don't know talk about Einstein. I jump to Oziewicz, yes, and it's very big and history. It's very important. Canonical ternary Oziewicz-Dragan relative velocity. We exactly see zeta before. Now is zeta orange vector and this explicitly formula for this. And now we see construct exactly canonical ternary velocity of Oziewicz-Dragan. If we have zeta, we subtract without zeta sigma, we get a red vector psi. His psi is exactly covariant formula of space like Oziewicz-Dragan ternary relative velocity. Its relative velocity, it seems quite complicated, but exactly it's not very complicated because this only the normalization factor. It's complicated, but it's only one number. It's not vector. It's only normalization factor. But this vector, it's simple orthogonal subtraction mi and nu, and which orthogonal to sigma, which term determine this orthogonality. History of Oziewicz-Dragan ternary relative velocity. According to my knowledge, these concepts defined only two people on the world. The first, Oziewicz, and the second, independently, Dragan. And this my only recognized this concept, and so I only understand this, not a lot of. Conclusion. All relative velocity in the special relativity, except binary, are ternary. They depend on the observer. This means they depend on the observer frame of reference in different ways. The first. The second, only the canonical ternary Ojevich-Dragan relative velocity is antisymmetric. This means that this relative velocity, probably the best the relative velocity, is the orthodoxical relative velocity. And the this presentation is only the definition of relative velocity without the rules for their composition. This proves the richness of Ojevich research program, which I call ternary special relativity, TSR. Thank you for attention. My email, this presentation is available on ResearchGate, and paper to this conference is available to ResearchGate, another paper, and arXiv the same, and conference proceedings I hope coming soon. Thank you very much.
Thank you very much, Professor Coulson. Quite interesting talk. I guess that it's impossible to go so deeply into all the research program by Professor Shevitz, but thank you very much. It's quite interesting. There are some questions that we have for you. One of our panelists wants to know about the magnitude of binary velocity versus magnitude of ternary velocity. Are they the same?
Ternary or I can see you.
Sorry, the question is the magnitude of binary velocity versus magnitude of ternary velocity. Are they the same?
Understand. No, it's general is not the same. It is not the same the Einstein velocity, Einstein-Minkowski or Einstein-Ojevich. It's different values.
Okay, thank you very much. Well, so if anybody wants to ask further questions, Gregory Coulson has given us his contact information, and you can download the presentation that he has shared with us in a few minutes ago. Remember also that all this is being recorded and you can check it on YouTube channel. But now, thank you very much. Now we have with us another speaker on the topic of theoretical relativity, that is this block of talks. And with us, we have Mariana Espinosa Aldama. And Mariana Espinosa Aldama will show us what she has done with the space-time theories exploratorium. Before I let her speak, let me read a short biographical profile of Mariana Espinosa Aldama. I will read this in Spanish. Mariana Espinosa estudió la carrera de física en la Facultad de Ciencias de la UNAM, fotografía en la Escuela Activa de Coyoacán, diplomado en divulgación de la ciencia en la DGDC, maestría en filosofía y comunicación de la ciencia en el Instituto de Investigaciones Filosóficas de la UNAM. Actualmente es candidata a doctora en Ciencias Sociales y Humanidad por la UAM Coajimalpa. Su trabajo está enfocado a comunicar cuestiones relacionadas con la astronomía, la física, la historia y filosofía de la ciencia, y siempre se ha caracterizado por imágenes en diversos formatos: dibujo, fotografía, video, infografías y visualizaciones de datos. Entre 2006 y 2011 fue responsable de la Oficina de la Comunicación del Instituto de Astronomía de la UNAM, así como coordinadora de la Oficina del Año Internacional de la Astronomía 2009 y coordinadora de la Ciudad de México y a nivel nacional del Festival Noche de las Estrellas. Ha producido más de una docena de festivales, exposiciones y congresos de ciencia y publicado decenas de artículos de divulgación y otros materiales impresos. Ella ha sido fuertemente inspirada por por los avances de teoría de la gravitación propuesta por astrónomos como Javier Hernández y Sergio Mendoza, por los trabajos de Cathy Burner de la Universidad de Indiana sobre mapas de la ciencia y por el giro pictórico del análisis de las teorías científicas, que se abordó en el Seminario de Representación y Modernización de la UAM, coordinado por Mario Casanueva. En su trabajo doctoral, ella nos propone una serie de redes conceptuales e interactivas. Esto está disponible en la web, ya nos mostrará ella, en la que relaciona los conceptos fundamentales de decenas de teorías del espacio-tiempo y la gravitación. Los dejo con Mariana Espinosa Aldama. She's going to talk about the space-time theories exploratorium. Please, Mariana, go ahead.
Thank you, Carlos. Can you all see me now? Can you hear me? Yeah.
Yes.
Thank you. Okay. Well, thank you so much for accepting me at this conference. I'm very honored to have the opportunity to show you what I've been doing the last 5-6 years, I think it is. And well, I'm gonna start sharing my screen. Okay, so I'm gonna start sharing this one. Can you see it? Yes. Okay, well, I have to confess that I never met Professor Shevitz. Actually, I had not heard about him before this conference. But now that I've been hearing all of your conferences and experiences with him, I think, well, we would have had a lot to talk about, and I'm sad that I missed him. But now I'm getting to know his work, and I'm very excited about it, because I think it has well, a lot of in common of what I think and I do. So yes, the talk today, I'm gonna show you really quickly the webpage that I have created with all these visualizations, and then I want to come back to this presentation and very quickly and basically just present what formal concept analysis is, which is the methodology that I use to create my networks, and how I choose my how do I build the contexts for such lattices using set theoretic semantic empirical structuralism. Then I will talk a little bit about the where I get my data, and if I have time, I will show you what all this process involves, and see a few patterns that I have seen in the networks, and to see if we can get something out of them besides you know, like nice order concepts. So the main questions that I wanted to answer in this with this work is, first of all, if I could create a network of visualizations that could organize all the fundamental concepts of physical theories, especially those behind gravitational theories, alternative theories. And this is because I was very close to the development of the work from Sergio Mendoza and Javier Hernandez, which are astronomers in the Astronomy Institute, very good friends of mine. And I was very intrigued about their proposals. And as I started studying, I found out that there were so many alternative theories of gravitation. And I just started, you know, like reading about them and trying to organize them in some ways. Well, I was amazed to find more than 100 proposals, different proposals. So what would be the best methodology to relate all these proposals and visualize not only their concept, the relations of theoretical concepts, but also in time series and in citing networks. So I've been doing that. And also, what are the different formulations and reconstructions of theories that I have to take into account so I can relate all these theories? And can I join them, and can I make like huge network of theories? And how can I do this? And also, will these visualizations show me patterns that allow me a better understanding of the internal structure of physical theories? And well, I hope to answer a little bit of these questions. And for this, we have to, go back to the basics. So now I'm gonna share another screen where can you see now where it says space-time theories exploratorium?
Yes.
Yes, okay. So this is the webpage. You can see it much better if you use Firefox. I still have a little work to do there, so you can see it in Safari or Google Chrome or something else, but you can see it much better in Firefox. And it's the results of my PhD work on studies of science. Actually, the PhD is called on social sciences and humanities, but I think this is way too broad to to say what exactly that I do, which could be said that I do visualizations based on philosophy and physics. So it's more like science of science, I would say. And here you have all these buttons that lead you to the different visualizations. I'm gonna start with the one which is on the bottom of the list, which is the gravity apple tree. And this one will lead you to a Prezi file, which it's taking a lot of time to load. It's a very heavy file, I think. I'm gonna leave it for till the end. This is the work that I started doing around 2014 when I arranged all these 100 proposals of theories, and they are arranged following the publication date of their of the main paper where the proposal was made. I'm gonna try to reload it and see if in a little bit it loads much better. There we go. Okay. Can you see the whole screen here? I hope you do. Okay, so I'm gonna give you a super quick tour here.
Yes.
The main idea is that in the in the bottom part in the trunk, you have Newton and 200 years of Newtonian theory, and then 1905 comes and we start. I'm gonna skip this part, and we start with all these theories of relativity, special relativity, Einstein, and all that. So in the center of the tree, I put the main concepts, principles, theories that would drive all of these other proposals. You have here the time series, which goes every 10 years, started in 1905. You have in green the name of the authors, the date where the publication was made, And if you go a little bit further, making a zoom, you can find some pictures that may represent some of the concepts that I'm telling, and also pictures of the authors. And along the lines of the timelines here, like in gray, you have crucial experiments and observations that that were really, really important in gravitation, and that would somehow constrain theories to keep growing. The branches are the theories. And but in some other cases, they might actually make grow new theories. Okay, I'm gonna just quickly go through this, showing this all of these works. For example, on gauge theories, numerical relativity, string theory, quantum loop gravity, all of these that come from the center from ideas of more dimensions of Kaluza and Klein, Einstein and Cartan with the torsion ideas. And also, if you go a little bit closer, you can find some links, like here. If you click into these links, it will take you to the PDF file for such publication. So my idea here was just to try to organize all of the theories that I was finding and trying to give them place according to the date of publication, and some relations like citations, like explicitly saying that their work was based on a specific idea, or citing another publication. But these are Javier and Sergio Mendoza from Astronomy Institute and their theory, and this is where I wanted to, like to find them a place in the map. So I hope I actually did. And this work was finished around 2016, but I had still like the sense that the fundamental concepts of theories were not really well connected, and that most probably this network was much more complex than what I show here. So this was like a first schematic view of all of the zoo of theories that I found. Okay, I'm gonna get out of Cressy and then go to the other networks that I started doing with formal concept analysis, and which I will explain a little bit more later. But I want to show you how these interactive networks, you can move them around. You can click on the different attributes that you have here and get some kind of further explanation. Not a huge explanation yet, but it does tell you what it is. Each node corresponds to a concept, and they are related hierarchically. And the attributes are divided in different classes. So we have the differential manifold, geometric objects, typifications, and conditions. I will explain this a little bit later. And also you have the models. This network, this lattice is for space-time theories. And the information was taken from Michael Friedman's Foundation for Space-Time Theories, with a little bit of input from Sotirius and Faraoni's F of R classification of F of R theories. And that allowed me to include the affine connection in this network and the metric affine spacetime. Okay, so another network that I have here is based on Mario Bunge's axiomatization of physical theories on his Foundation of Physics of 1967. And what you can see here, yeah, if you click on either attribute, what it will show you in the information window here is all of the axioms that correspond to such concept, to such attribute. So it is completely based on his axiomatization. And if you look for axiom CM1.7 in his Foundation of Physics, you will find exactly this information. So this is a companion for reading such books as Bunge's Foundations of Physics and Michael Friedman Foundation of Spacetime Theories. So Michael Friedman says that he calls spacetime theories all of those theories that involve describing an object moving through spacetime. So it's almost everything, but not everything. Almost all theories in physics, but not all of them, because actually not all of them talk about spacetime. Okay, so here I have another network which includes Sergio's extended gravitation, which is a Mondian theory. And it's a Mondian theory because it includes Milgram's acceleration constant, which is actually, let's see here. Okay, so in these networks, if you click in a node, it will show you its parents and its children. The parents would represent all of the foundations of the model of the concept that you are clicking on, and all of the models below would be called specialized models. Okay, and finally, I'm going to show you here which the one that I call the holon of theories, where I have included all of the theories that I have found formulated in a Lagrangian set theoretic formulation, all of them based in a 4-dimensional manifold, which be the attributes for the top node here. So this is very interesting because we can find, for example, theories based on the Leibnizian spacetime, Galilean spacetime, Newtonian spacetime, which includes only here kinematics with absolute space and time. For example, we have here all the theories under metric affine spacetime. We can find also local theories, since some of the theories extended gravity are considering non-locant properties for their equations. Different kinds of metric theories, for example, those which are based on a geodesic law, but also metric theories which are based on a metric tensor, those that are in a Lorentzian spacetime, and also F of R theories, which is another way of calling metric theories, which would be pure metric theories. And also we can see that there is some kind of pattern on the alignment of the models in the theory, in the lattice. Like the most old theories are on this side of the lattice, and the Newton-Cartan gravitation, it's getting closer to the center than metric theories with eta, which is the metric tensor with no curvature. So this is these other theories, and the more modern theories are on the left side, right?
You have 5 minutes left, Mariana.
Okay, thank you. So I'm so glad that I started showing you the whole loan and all of these networks, because I'm sure that you are all familiar with formal concept analysis, and I didn't want to waste all my time talking about these basic concepts, but I will just run around it very, very quickly. I'm gonna stop sharing this and now start sharing back to my presentation. Okay, so, well, the ideas of formal concept analysis were developed at the end of 1970s and 1980s by Rudolf Wiley from the Technical University of Dartmouth, and holding the philosophy of Hartmut von Henting, a German educational reformer. And they would say that sciences have to examine their disciplinarity, and this means to uncover the unconscious purposes, to declare their conscious purposes, to select and to adjust their means according to those purposes, and to explain possible consequences comprehensively and publicly, and to make accessible their ways of scientific findings and their results by the everyday language. So I hope I'm trying to do this. So a formal context, very quickly, is composed by objects and attributes and incidence relation. And we have two operators, one that would take you from objects to attributes, and another one to attributes and to objects. And when this relation is used in a composed way, if it returns you the same result, if you start in objects like Tierra and Marte, which are pequeños cercas, small and close, and you go back to see which ones have those attributes at the same time, it returns you to Tierra Marte. Well, that is a closure. So this is a closure operator. This would be all of the concepts that would give you the analysis, and then you order them by this double implication of partial order. And here, well, this will give you a lattice, but we have to remember that not every network is a lattice. A lattice, you have to have, for each two nodes, you have to have a minimum and an upper and a lower bound. And if it's not unique and does not exist, then it is not a lattice. So labels are attributes and objects. Nodes are concepts. Concepts are made of, it's a pair of pair of sets, which are attributes and the extension and the intention is called. You have head-change relations. You have a directionality, which is vertical, but parsimony on the development of theories lets you see that they start, you have them accommodated in such a way that you don't have big jumps from one place to another. So concepts evolve parsimoniously. That's what I have observed. So formal concept analysis is used in data mining, collections, browsing, linguistic analysis, psychology, software engineer, artificial intelligence, and analysis of social networks. It's a recursive process. So you say, I have a database, make this analysis, you have a display, visualization, then you have to interpret and see if your results are valid. If they're not, you have to make an exploration. That would be an attribute or an object exploration, and start again. Here I give you some very good directions, web addresses, where you can find very good information. The webpage of Utapris is full of information about formal concept analysis. And I think that might be all the time that I have. Maybe just go to the final remarks. Okay, very quickly, I'm going to show you here. This is my database. I have axioms. I have the class of axioms, the label that I'm going to put on every attribute, and then the attribute, because let's remember that not every software reads any labels, so we have to be careful there. And yes, my final remarks. Well, all these contexts that I have built are departing point for mapping numerous other theories that we might be interested in. A perfect example of the rigorous, exhaustive mathematical and conjoint treatment is that of Mario Bunge and of his Foundation of Physics, that is a semantic set theoretic approach. It is ideal for collecting the data necessary to shape all of the contexts. The formal concept analysis is a methodology for visualization and analysis of concept that is useful for the representation of theoretical structures. And this, I think, it has not been very well exploited in philosophy of science and in physics. It has been more exploited in data mining and other kinds of classifications, but not for the structuralisms. I think there is very few work on that. And yes, multidisciplinary knowledge is required to do this scientific philosophy that we call it. Axiomatizations and reconstructions that follow the same criteria can be put together to form a great structural scaffolding of physics and other sciences. The lattices allow us to identify that the elements in common correspond to the characteristics of a theory, as well as to the shared characteristics of such a geometric, algebraic, and topological, as well as the serological principles and material basis, which I could not talk about. But it's an interesting topic to read about in the Foundations of Physics of Mario Bunge. And finally, these visualizations can be of use and interest for students of physics, philosophers of science, mathematical structuralism, and complexity sciences. So I leave you here some bibliography that I can copy to you in the chat if you're interested in. And yes, open for any questions.
Thank you very much, Mariana. Pretty beautiful, beautiful work for a lot of years. And I guess that is very kind to the spirit of Shevitz. And well, there are a lot of possibilities. So if anybody has any comment or any question, well, you can write it in the chat or in the question and answer chat box. And we will send all these comments to Mariana, because we are running out of time. and then we have another speaker. But anyway, just any comment from the people on that is live now in Zoom? We go with our next speaker. Okay, well, so we will go on with our next speaker. It's a very beautiful work, Mariana. I really enjoy it, and I guess that all of them might have. So, well, now for our next talk, our next speaker is Romualdo Brasis. Well, Romuald Brasis, and he is going to share with us his perspective on classical relativity and quantum relativity versus special relativity. He has prepared a video for us, and we will show this video. He is with us, Romuald Brasis, and he will be open to questions and discussions after this video that will be shown. So let's go ahead with the video by Romuald Brasis, please.
Good evening. I'm Romuald Brasis from the University of Vilnius. I would like to thank the organizers for inviting me to the conference dedicated to the memory of Professor Zbigniew Osiewicz. I greet you from his hometown. Cordial thanks to my Mexican colleagues, especially Dr. Hilda Maria Colin Garcia, for their exceptionally warm care of Professor Zbigniew Osiewicz, our genius compatriot. Professor Zbigniew Osiewicz influenced me in 2003 at the Polish-Mexican workshop on mathematics in Wędlewo near Poznań. In his lecture on relativity, he remarked that the Lorentz transformations do not meet the requirements of group. This deep remark prompted me to look at the special relativity from the new perspective. I reviewed the issues of relativity in the textbooks of physics for the School of Lithuania and Poland and wrote a couple of papers on it. Professor Zbigniew Osiewicz encouraged me to continue the research and opposed some my consideration, as he was convinced that the opposition is the only driving force of science. Particularly, he remarked that in modeling the Doppler effect and light pressure, I had omitted Bradley aberration. Indeed, Bradley was named in Osiewicz's works, but surprisingly omitted in the school textbooks and in Einstein's seminal article. It was start of my research into the genesis of the concept of relativity. Aristotle's idea, translated to modern notion, tells that the four kinds of matter are immersed in the fifth one, aetheros, a heavenly subtle substance, and a universal light-carrying medium. James Maxwell defined the electric and magnetic permeabilities of the aetheros. Also, other properties of the primordial substance still remain undisclosed. The hypothetic universal medium does not resist against motion of massive bodies, so it should be superfluid. Copernicus awoke from blissful ancient sleep, and humanity faced the necessity of navigating the universe with no possibility of a stop. Everything is motion, in motion. Where is the real place of Earth, planets, comets, and so on. How long do events last of them? Copernicus was conscious of the universal gravitation law and the law of inertia when he stated the importance of role of selection in the relativity of motion. Our small Earth can force the rotation in 24 hours much more massive bodies like the Sun and countless stars. In this report, the roles of three bodies are considered: the medium carrying the disturbances, the source body emitter disturbing the medium, and the observer absorbing disturbances. Galileo articulated the principle of relativity. The physical laws remain unchanged, independent of whether the observer laboratory being still state on in uniform rectilinear motion. Galileo did not exclude light. Romer discovered the shrinking by 15 seconds and dilation by 15 seconds of the Jupiter satellites Io eclipses duration depending on whether the Earth moves toward the Jupiter or runs away. Surprisingly, this discovery of the relativity of a process duration is omitted both in the textbooks and in the Einstein's special relativity. James Bradley discovered that the perceived Christian Doppler said that the time lapse between two disturbances detected by a moving observer is the homographic function of the observer's velocity raised to the disturbance velocity as given by the formula 1. And when the source is moving and the fixed observer, the time lapse is the linear function of the set velocity ratio to the disturbance velocity as given by equation 2. Doppler formulas express the relativity of a perceived process duration limited to the source and observer's motion along the line connecting the two bodies. Einstein postulated that the effects must be independent on whether the source or the observer are in motion, equaling Doppler's equations by introducing an adjustable factor gamma as given by equation 3. Gives the value of the factor the same as in the Lorentz transformation. It is given by equation 4. And in this way, the special relativity prohibits objects' motion with velocities exceeding the signal carrying disturbance velocity. And the perceived position of fixed stars is set by the Bradley aberration theorem by the formula 5. We transform the formula in terms of the complementary angles phi in order to see that the Einstein claimed the most general formula of aberration 7 is in fact the classical formula 6 expansion in series of the small parameters VD2C. So it is not the most general formula. The perceived duration of a process in a fixed source is a little bit complicated by the different delay of the signal sent at the beginning of the measured process and the end of the process. Here is the star, here is observer at the beginning, and here is the observer at the end of the measurement. And the duration is, process duration is given by equation 8, and the delay times are defined by equations 9 and 10. The perceived duration shall be mapped on the observer's clock data set, that is t plus tau 0 plus the delay of the second, the last pulse. The graphical map is a smooth function, and perceived duration is short in the area of observer's approach to the source, and long in the area of the moving away. If the first disturbance is emitted at the instant t0, when the moving observer passes by the pericenter, then the disturbance will catch the observer at the distance given by the formula 11. Here appears the gamma factor, which indicates that the disturbance, including light, will never catch up with an observer who is in the instant of disturbance emission at the source and moves faster than this disturbance. Perceived process duration in a moving source is different from the previous one. I'm not going to the details. I draw your attentions to the equation 12 that gives the time duration. The function should be mapped on the observer's clock, and in spite of apparent complexity, it is a small function of the time. There is no gamma factor, no restriction on the spacecraft velocity. And about telling about the aberration, Bradley said that the angular position of a fixed star perceived by the moving observer is shifted toward forward from the star's real position. And in this work, we get that the angular position of a moving star perceived by a fixed observer is shifted backward from the star's real position. And it is worth noting the negative duration equation 12 gives the negative values of the perceived duration of a process when the source object moves faster than its emitted disturbance. The latter emitted disturbance arrives before the earlier emitted one. Observer can not perceive the approaching superfast object until it hits or passes by the observer. Special relativity with its restriction of the velocity prohibits such a phenomenon to occur. And a quantum concept starts from Nikolaus Umov, then Adolfo Bartoli, and Peter Lebedev, and finally Max Planck, who proved that the quantum energy is the linear function of the disturbance frequency. So the relation discovered by Planck allows for a simple and convenient evaluation of the elementary disturbance momentum and a calculation of the aberration angle and the disturbances pressure from the act of particle-like disturbance collision with the screen. And here is the example of such calculation of disturbance pressure. The pressure is negative in the area of the observer approach to the source, because the pressure acts then so as to stop the motion, and when the observer passes the source, then the pressure force is positive, tending to accelerate the observer's motion. The equation, governing equation 13, includes the time duration that should be taken either for the fixed source or the fixed observer, and the angle of aberration accordingly. Einstein's formula 14 contains the gamma factor square that is absent in the classical quantum formula, and therefore the special relativity contradicts the quantum relativity as well. And in reassumption, the algebraic approach presented in this report allows for modeling of the duration and place both of the high frequency processes and single events. Classical relativity predicts time reversal, that is negative duration of events at super high velocities. It means that negative quantum energy, the possibility of light emission by the super fast objects, and the impossibility to detect an object approaching with the superluminal velocity is another challenge arisen by the classical relativity. However, the question of superluminal velocity remains open because the properties of the universal medium at present time are not known. I would like to thank the conference staff and international audience for their patient attention until the end of the all-day session, which in my town turns out to be nearly all-night one. Thank you. Gracias.
Muchas gracias a la presentación de Romuald Brace's. Thank you very much to Romuald Brace's presentation. So Romuald is here. So if you have any question for him, you can say this question live. We have a few minutes. Or if you want to type it, you also can type it and we can read it. So please, questions, welcome.
No question.
Can I question? Yes. Do you hear me? Yes.
I'm not sure that I see you.
Yes, we can hear you.
But I hear you.
Okay. About Doppler effect. If you defined alternative equation for Doppler effect, the first question, and if yes, if it's different for axial and transverse Doppler effects. Okay. Well,
Doppler effect is I call it I don't write equations for frequency because I wrote expressions for the time duration, but it is just the inverse time duration is a frequency. So all these equations that I demonstrated represents the Doppler effect, including the offline motion of the star or the observer. And as I understand, your question is about the so-called transverse Doppler effect. If these equations that I presented include this case, but I wanted to remark that let's say if the source or the star, or let's say generator or emitter of perturbances generates short beep, just short signal, and the observer passes by the source, the signal will catch the observer far away of the place where you can say that it is transverse, because it is either the situation is that if you generate the signal in some place, the observer is already not in the same place. The observer moved away. And so on. So this question of transverse Doppler effect is more or less, so to say, not very important. Conceptually, it is not very important. It is included in the equation I presented here.
Thank you very much, Roland. Garrett has another comment. Please, Garrett.
I was just wondering exactly is there any connection to this idea of of Oshevitz's idea of binary and tertiary of relativity, of special relativity? That was the lecture before.
Well, my discussions with Zbigniew Osiewicz were very motivating me. However, I went, so to say, my own way in order to understand what is the relativity theory, what is the special relativity, what is the classical relativity. And I started from the school textbooks, from the very basic things. So I was afraid that if I'll go through the high mathematics that is used in Osiewicz works, and I will spend a lot of time in going through the complexity of the mathematics, and therefore I selected this as simple as possible way of going through the ideas of relativity. So Zbigniew Osiewicz role is seminal for me. He somehow transferred me the interest in these philosophical problems of relativity.
Thank you.
Thank you very much. There is another question. Michael Heather questions is the following: if the universe is not quite Euclidean, how does that affect all the equations?
Well, I don't consider the general questions of relativity, including the general relativity. I consider just the situation that the observer or absorber and the generator or the star are moving in a medium, something like the airplane moves in the air, and the velocity of the airplane is measured relative to the air. The pilots need to have the velocity relative to air in order to know whether the airplane can move or not. And they measure the pressure, the velocity measure with comparing the dynamical and static pressure of air, meeting the airplane. The same is with the, say, with the vessels in ocean. The velocity is quite easy measurable, but the position is not very easy measurable. And so to say, I try to keep this line of thinking that I know separately the velocity of the observer or the velocity of a star, and I know the velocity of the disturbance. But what is important, I need some interaction, because without an interaction, these velocities don't have any meaning. So when the disturbance collides with the observer, then I need to know their relative velocities in order to calculate what will be the relative momentum and what will be the force exerted by the disturbance on the observer screen. And therefore, for me, it was very important to catch the idea how to evaluate the pressure of disturbances, because the pressure is something that connects my kinematics consideration on the one side with, let's say, future considerations of dynamics. And the pressure is the link between the kinematics and dynamics. What was for me not very clear, why the special relativity pay so much attention to the kinematic part. Einstein, in his seminal work, evaluated the pressure of radiation, and it is very important that he tried to make a synthesis of the classical works of aberration, Bradley's aberration, and so on, and he included also consideration of the pressure and force, and so the theory became more physical, because in let's say in Romer observation of the Jupiter eclipses, and in Bradley observation of star aberration, the forces, the pressure was not considered, but Einstein somehow, to my mind, went the wrong way when he equalized the case of the moving star and the case of moving observer. These two kinds of phenomena, the two processes, are identical only when the velocity is zero, nearly zero, only then. And when the velocity is growing, the discrepancy between the theory that equalizes both the cases and the classical approach, the discrepancy will grow. So it is my thought that I just wanted to consult you and let's say hear your response. Perhaps I should stop considering, or I should continue the consideration in future. This is the point why I am with you now this evening.
Well, thank you very much, Romuald. I guess that there will be further chances to continue with these talks. Now for today, it's been all our journey. So we thank you, Romuald. We thank all of our speakers and all of our attendees for being with us today. Since the very morning to this afternoon, we hope that you enjoy this journey, and we really expect you to be with us tomorrow since 9 o'clock a.m. That is -5 GMT time, and we will continue in this journey talking about non-commutative geometry and differential calculus. That's going to be tomorrow's first block of talks. So thank you, everybody, and hope we can continue with all these talks very soon. Thanks a lot, and see you tomorrow.
Thank you. See you tomorrow, everyone.
Yeah, thank you.
Bye.
See you tomorrow.
See you, Hilda. Bye.
Surely it was very exciting journey, Jesus. Thank you very much for organizing, for selecting such marvelous works. Yes, it was fantastic. Thank you very much.
Thank you to you and to everybody. I think this was a work of everybody in this Congress. Yes. Mm-hmm.
Yes.
Okay. See you tomorrow.
See you
Thanks.
tomorrow.
See you guys.
Bye.
Bye. Bye, Larissa.
Bye. Gracias. Thank you for your comment. Thank you very much.
All right. Bye.
Bye.
Okay.
Slava, quando va a tener su plática?
Hasta el viernes.
Hasta viernes, ¿ya?
Ujú.
Vamos a tener una jornada muy, muy pesada, pero sí muy nutritivo, es una fiesta intelectual. Y gracias por the